Bon dia, bonjour, hello. I am Jean-Paul Brasselet. Eu sou professor de pesquisa, diretor de pesquisa do CNRS na França, emeritus, e também na Universidade de Aix-Marseille, em Marseille, no sul da França. Então, eu tenho o grande prazer de dar este curso para você sobre classes características. Eu sei que todo mundo está mais ou menos confinado, ficando na casa, então o que vamos fazer é cruzeiro no tempo e no espaço. Eu vou dar meu curso em inglês, então eu vou falar inglês agora. So I will, as I said, I invite you, in fact, for a cruise through time and through space. And so we will meet a lot of people, some people you know, some people you don't know, we will see. And this cruise will start in 370 before Christus in island of Samos in Greece, where we meet Pythagoras and Thales, you know. And they are playing with some dice. So that is the first stop for our cruise. We go to Athens with a boat, and we meet there more people, Theaetetus of Athens and Plato. And they are also playing with dice. So I will show you. So this is the dice the dice they are using also Plato and Theaetetus in Athens. Maybe you don't know Theaetetus, you will know during the course, we will see. So in fact, what we will do is taking the boat, we are here in Samos, in Greece, in this island here. We came to Athens, and now we go to Syracuse, in Sicily, in Italy. There we meet a guy who invites us for a walk on the beach. It's Archimedes. I think you know also this guy. And we stay in Sicily for a long time because it will be now 1436. And we meet Italian priest, Francesco Maurolico. This will be completely a novelty, a scoop for the course, because I will give you some explanations that you don't find in books. The fact that Francesco Maurolico, he has discovered that for all these plateau polyhedra, plateau solid as they are known, the number of vertex minus the number of edge plus the number of faces is always 2. And that is a very important observation well before Euler and before also Descartes. So now let's go to Descartes. We will see, this is Europe at the time of Descartes, which is absolutely not the same picture of the map of Europe that you can see now, but we are in the time of Descartes. We go from Sicily and we go to here, Stockholm in Sweden. Where is Descartes? So we will follow the manuscript of Descartes. I will explain this to you, going to Paris, going to Berlin, going to Hanover with Descartes, with Leibniz, he came to Paris, with Euler, and also with Cauchy and Legendre in Paris. So all these guys, they prove and they speak about the famous Euler formula, the fact that if you take any polyhedra, convex polyhedra in dimension 3, the number of vertex minus the number of edges plus number of faces is equal to 2. This you know very well. Okay, so I will come back here. And now we continue our trip. We stay in Paris for a time, and we meet Poincaré. Poincaré is there for funerals of Victor Hugo, you know, so that gives you the idea of the time. It's 1885. And Poincaré invite us to look at that time it is the beginning of construction of Eiffel Tower, and also beginning of the first metro in Paris. It's good to know this time. And Poincaré explained to us that he is writing a very nice paper about what you know, I think, as a Poincaré-Hopf theorem. Poincaré-Hopf theorem says that Euler-Poincaré characteristic is equal to the sum of indices of the vector field with isolated singularity on a smooth, compact surfaces for Poincaré and spaces manifold for Hopf. So that is very important, that the Euler-Poincaré characteristic is the measure of the obstruction to construct a vector field tangent to the manifold. And that is the beginning of characteristic classes, really. Hopf asked one of his students, Stiefel, to continue this and to look at what is the obstruction to construct a field of airframes tangent to the manifold. Airframes, air linearly independent vector on the manifold. And Stiefel did this, and also we learned that another guy, Whitney, in the States, is doing this. So we take the boat from France to States, and with Whitney, we learn what he did, and he explained to us that he is able to measure the obstruction to construct an airfield tangent to the manifold. Okay, so during a long time, this was the point, but Chen did another paper about manifold on the complex situation. So that is the beginning of characteristic classes for the complex situation with Chen. And this is very important because we will see that Chen classes, which compute the obstruction in the complex case, are used a lot in physics, in string theory, superstring theory, quantum field, and a lot of application in physics. So it's a very important point for characteristic classes. That is for manifold. And during a long time, as Poincaré shown that Poincaré-Hopf theorem does not work in the singular case, many people think that it's impossible to do with singular varieties. And it's a fantastic work by Marie-Hélène Schwartz. You know that maybe Laurent Schwartz, but the wife of Laurent Schwartz made fantastic things. And she worked with the singular varieties. And she was able, we will see, how to construct Poincaré-Hopf theorem for singular varieties. And she had very nice ideas to do that. And this was in 1965. Then another guy, Macpherson, did that on a point of view more axiomatic, I will say, answering a conjecture by Deligne and Grothendieck. And we will see that these Chen classes for singular variety by Marie-Hélène Schwartz and by Macpherson are in fact the same. And so that will be the reason for which now they are called Chen, Schwartz, Macpherson classes for singular varieties. Fantastic work by Marie-Hélène Schwartz, which shows the meaning of these classes. And this will be one important point during my course. I will give more the meaning of things than axiomatic definitions. We will see also axiomatic definition. Axiomatic definition allows to compute, but no, you don't understand the meaning. The obstruction theory that I will use allows to understand the meaning of these classes. Not too much to compute, but the two are necessary, okay? Axiomatic computation and also the obstruction theory. So we will see also application of this and using of this. I would like to dedicate my course to Roberto Callegas Bedregal, maybe you know him, professor in João Pessoa, who died with a virus on 7th of April this year. And he was a very nice mathematician that I've known. I discussed a lot with him, so I will dedicate my course for him. Thank you.